Right, indeed. I'm Robert Watson. I would list the long list of co-authors, but unfortunately that would go on for a while. I'm joined by co-authors from SRI International, University of Cambridge, Memorial University, Newfoundland, Google, and UCL in London. This has been, thus far, a 5-year project, and if you divide the number of minutes for this talk by 5, you'll discover we get 2 to 3 minutes per year of research. So there you are. Right, so I'm going to talk to you about CHERI, an architecture to support scalable compartmentalization. But to do that, I first need to tell you, or perhaps remind you, about what compartmentalization is and why we do it. So software compartmentalization is a mitigation technique by which we decompose software into isolated components, and we delegate to each of those components only the rights they require to operate, so motivated by the principle of least privilege. The idea there is that when there is a vulnerability in one of these components, the attacker is going to gain some privileges in the system, but not all privileges. And this is a widely deployed software technique in practice, although perhaps not as widely as we might like. Oops, there we go. I have the same problem our other speakers have. You can't easily see what it is that's up on the screen. So one of the problems that we have with software compartmentalization is that there is actually no single compartmentalization. There we go. No single compartmentalization. We often speak of an application as being simply privilege separated or compartmentalized, but actually you get a range of design choices and trade-offs between performance, security, and complexity. So if we want to increase security by making the compartmentalization more granular, we're going to have to pay a cost in terms of complexity and performance. So an example of this might be in Google's Chromium web browser. If you have Chromium running, then you're going to be having sandboxing going on. Different tabs are running in different sandboxes. But we're going to pay some architectural costs and software costs in order to have that. We could have more granular compartmentalization if we wanted, but we would then pay a great deal of additional performance costs. And it turns out a lot of this performance cost comes out of the process model that we're implementing compartmentalization with. So there are really two costs that we're interested in. The first is a performance cost that comes out of the hardware-software interface and the process model. So when you create processes, you pay the cost in memory for page tables and for memory access to them on every virtual address access. And then we have a translation look-aside buffer that's going to cache the most frequently used mappings. And one of the problems with the TLB is not only is it a very expensive hardware structure, it's an associative structure, but also it's quite bounded in size. When we start to compartmentalize software, we're going to have more shared memory. We actually get multiple entries in that cache for each underlying physical page of memory that's being accessed. So there is a nasty scalability problem. And second of all, we have a problem with programmability, which is that we force programmers to work with multiple address spaces at a time, which makes it quite hard to write software and debug it. But we also force them to make these compartments communicate with each other using inter-process communication, which is sort of often message passing, sometimes a blend of message passing and shared memory. But either way, it's quite hard to debug and understand. And if you've used RPC, you will probably have suffered with the authors of many of these applications. These kind of problems show up when we use compartmentalized applications today quite visibly. If you use Chrome and you have sandbox tabs, you'll discover that as you increase the number of tabs, eventually Chrome decides that the performance overhead is excessive, it's scaled to the hardware available on the machine, and will start combining different tabs in the same sandboxes, which of course defeats the purpose in many ways of having granular sandboxing. And that is a direct result of the design choices that are present in hardware and low-level software. So if we would like to promote more granularity in compartmentalization, which would give us more resilience to exploited vulnerabilities, then we would really like to be able to have many more of these compartments. So we might ask the question, how could we accomplish that using architectural features? I'll give you another example. In my previous slide, when I told you about compartmentalization, I showed you the gunzip application in Unix, which normally runs in a single process. When we compartmentalize it, we break it into multiple processes. We learned something interesting when we were doing that, which is that gzip as an application compartmentalized very efficiently and very well, since its higher level APIs use file descriptors, which are easily delegated using conventional process model. But if we wanted to put the compartmentalization where it was most necessary, which is say we'd like to put it in the zlib library, which suffers most of the vulnerabilities. That way, if we compartmentalize zlib, every application would benefit from the compartmentalization. We couldn't do that, and it was for both of these reasons, which is to say the library interfaces were not suitable for use with inter-process communication, and the programmability challenges were substantial. So let's turn to the next slide. So over the last couple of years, we've published a number of papers on the CHERI capability model. So in 2014, we published a paper at ISCA on a fine-grained in-address space memory protection model based on the idea of capabilities. So you may remember that a capability is a token of authority, right? It grants and delegates rights. And if you don't have the capability, you can't construct it. So what we did was we implemented within address spaces the ability to use capabilities instead of pointers to reference data. And this gave us some very strong protection properties. In particular, we gradually shifted pointers out of the general purpose register file and into a capability register file that offered monotonic decreases in rights and other capability-like properties. And we also provided tagged memory that allows capabilities to maintain their integrity when stored outside of the register file in RAM. And we got from this, among other things, integrity protection for pointers themselves, extremely strong integrity protection, a measure of control flow integrity, because we can also use these capabilities for jump targets and return addresses and so on, and also bounds checking, so the ability to prevent overflows of buffers and a variety of related kinds of problems. The real contribution in the paper, though, is the hybridization with the memory management unit, which is to say this model composes very nicely with a virtual address space model. So this allows us to experiment with capability system designs within a conventional architectural design or operating system design. This spring, we published another paper, and this was on using the C programming language capabilities, which is to say asking the compiler to generate capability instructions and use capabilities instead of using general purpose registers. So we were able to have existing C code structures map into a very fine-grained memory protection model with a high level of compatibility. And to do that, we had to merge ideas from fat pointers, which have to do with the fact that in C, a pointer may range throughout the bounds, or perhaps in fact beyond the bounds that are present for the buffer that it's in, and maybe come back in again. And we need to merge those with capabilities to get the strong integrity properties. So we were able to use a compiler to generate these. And of course, we're now able to run with these on top of CHERI, which really begs the question, if existing fine-grained compartmentalization is based on memory protection using the MMU, can we construct similar kinds of structures using the capability model within address spaces, which might be a better way to accomplish fine-grained compartmentalization within an application? So I suppose it begs the question, and the answer is unfortunately obvious, or we wouldn't have written the paper. So let's take a look through a couple of the differences between virtual memory and capabilities. But as I tell you about these differences, I want you to remember that in CHERI, we can do both, which is to say, whenever we find a memory protection problem or a compartmentalization problem, we're going to pick one of these two technologies or perhaps combine them to accomplish our goals. So the first question we have to ask for the two different models is, what can they protect? What are they good at protecting? Well, virtual memory is good at protecting virtual addresses, which is to say the underlying storage of data inside an address space. It does so at a very coarse granularity, that of pages. The capability model allows us to protect the references to data rather than the underlying storage of data. And this turns out to be quite programmer friendly, because often you take a reference to an object, you pass the references around, you want to limit what they can do. Perhaps this one is a read-only reference, whereas the other one is a modifiable reference, or maybe we will subset access to a portion of memory. So with capabilities, we can use them to describe C code and data structures, so much more focused at the internals of an application, whereas paging is focused on the overall structure and virtualization of the application. On the hardware side, we retain access to a memory management unit and a TLB, sort of conventions of virtual memory and virtual addressing, as I described. On the capability system side, we have capability registers, which are going to gradually displace general purpose registers as the storage for pointers. And we also make use of tagged memory, which comes at a small but measurable overhead. So we use a 1-bit tag for every 256 bits of memory. All of these systems come with costs. On the virtual memory side, we often have the forgotten costs of the virtual memory subsystem. So for example, not just the hardware cost of the TLB, but also quite large page tables in memory, continuous lookups, and also on multiprocessor systems, we have to perform inter-processor interrupts in order to revoke memory on remote processors. On the capability side, we're going to incur a per pointer overhead, right? So fairly measurable in terms of cache footprint and so on. And we're also implicitly going to take an additional cost in context switching, because we have to preserve this additional state. So that was the work we had presented in our previous papers. What we add to it in this paper is applying the idea to compartmentalization itself. So virtual memory is quite good at maintaining maybe tens or even hundreds of simultaneously active processes, which I mean processes that are continuously running and context and switching between them. But at some point, your TLB runs out of juice. With a capability model, we would like to be able to maintain thousands or tens of thousands of compartments, one for every image read in your web browser, right? Entering and exiting it every time we process an additional row of pixels. For domain crossing, conventional systems use inter-process communication. I've already told you that is problematic from a programming perspective. We're going to model our invocation system on function calls, try to have a constant overhead on the cost of a traditional function call. And then finally, they have quite different optimization goals. The focus of virtual memory is really full isolation and full virtualization of a system. We're interested in a model that is promoting memory sharing, which is to say lots of memory moving back and forth between components, so across library interfaces and so on, and extremely frequent domain transitions on the order of magnitude of function calls. So an ambitious set of goals. I want to talk to you briefly about how we're going to approach this from an operating system perspective, which is really the focus of this talk. So in a conventional system, you might have a memory management unit, a set of processes able to run applications that are linked against libraries and so on, all in the same address space. We're going to continue to support that on the left end of the scale, only we're now going to allow you to have libraries that make use of fine-grained memory protection and compartmentalization internally, invisible to the surrounding application. This is going to allow us to deploy compartmentalization in libraries like libping or zlib transparently to the consuming applications at a binary level, which means that if you have existing, for example, Android apps that are using native code libraries shipped by the vendor, you, the vendor, which is say Google, could in fact deploy these features internally without affecting the binary structure of the calling application. If we move a little bit further along this spectrum, we're able to use what we call a pure capability application, one linked and compiled to run entirely using capabilities, fine-grained memory protection, and so on. But we're going to allow you to run existing binary-compatible libraries inside of sandboxes inside the process. So we're going to be able to support legacy binary-only libraries that may be made available by vendors. CHERI can also support one more model, which is to move to a complete capability system approach, where we have a single virtual address space spanning the entire system. And again, we're able to run both pure capability code and also legacy code. So I should tell you briefly about these capabilities, since they're the underpinning for all of this. So in our prior papers, we've described a 256-bit architectural capability, which is to say the instruction set exposes this as a set of 64-bit values and permissions and so on. Capabilities are references to data. So they're a lot like pointers, only not only do they have a pointer in them, but they also have a base and a length. So they're able to describe bounded regions of memory. And in the prior work, we've described this as a monotonic model, which is to say you are able to take a capability and reduce the things it refers to, but you're not able to expand them. You can rederive capabilities from another capability with more rights, but you can't simply take a capability and expand it. And this is sufficient for us to start building strong compartmentalization on top. There's one more bit you should know about, and that is the tag bit. This tells us if the integrity of the capability is being maintained. If you do anything that violates the integrity of the capability, we're going to clear the tag bit, which means it can no longer be dereferenced or, in the new model, invoked. So we're going to add another bit, which is the sealed bit. It's going to take our monotonicity properties and now give us the ability to say this entire contents of this capability can no longer be modified. This is going to allow us to implement encapsulation. So you have a reference to an object. You're no longer allowed to manipulate the reference. It has been sealed, so you can't dereference it. We're also going to add a new object type. This is going to allow us to take code capabilities and data capabilities and atomically bundle them together, so that if we have an invocation mechanism invoking an object, we can now specify the two in tandem. And then finally, we're going to have a hardware-optimized call and return instruction set that are going to perform some number of checks in hardware, but at the end of the day, throw an exception to software to allow it to provide software-defined portions of the domain transition mechanism. And all of this, as I said, is with respect to a virtual address space. So these are the primitives we need to perform compartmentalization. We're going to set up the virtual address space, which is the central vertical bar there. I don't know if I have a working laser pointer. Not that I can easily draw with. The central bar is the virtual address space. On the left-hand side and on the right-hand side, we have two capability register files. They're going to be associated with threads. Each thread, as with general purpose registers, will have its own capability registers, and they define the effective protection domain that's implemented. And we're going to use this to implement an object capability model, which is to say we're going to have objects in an object-oriented sense referred to by capabilities. We can then delegate them around and invoke them and so on. And when we use the word encapsulation, that is the kind of encapsulation that we mean. When we start up a process, our libCHERI library and user space is going to be able to load and link additional classes, and it's going to be able to instantiate objects. But unlike conventional language runtime objects in C++, these are going to be compartmentalized using the capability model. So I've mentioned every thread is going to have a capability register file. This is going to describe its current protection domain. When we perform domain transition, we're going to do it within threads. So we're not going to have to enter the scheduler or do a number of other complicated kernel functions. We're just going to transform the register file. And what we're going to do is we're going to unwrap these sealed capabilities using the kernel's privileges, allowing us to transition between mutually distrusting domains in user space. As I said, we're going to use an exception facility, which is to say it's going to be partially software defined. But the most expensive bits of this structure are going to be things that we can do in hardware, such as checking permissions on capabilities, unsealing, and so on. What we're going to try to leave to software is only memory access. We use a RISC model, and we don't want to combine various kinds of operations with memory access. In our CHERI BSD model, we implement something called a trusted stack, which is a call stack of all the invocations we've gone through so far. But we could actually implement many other different kinds of security models. So we provide a synchronous call return mechanism, but if you wanted to, you could do an asynchronous model, perhaps based on closures. So let me show you an example of this. So normally when we enter the process, when it first starts up, we're going to grant the code ambient authority for its address space, which is to say it's going to be able to run using regular, in this case, MIPS instructions, and then begin to set up security domains. We're going to be able to make synchronous function-like calls into various objects that we've instantiated using libCHERI. And when we do that, we perform a ccall instruction. It takes us into the object, which runs without any privilege, or only the privileges we delegate to it. And then if it needs to, it could call into other objects. So this is a recursive model. And we can also call back into an ambient object, which can then perform system calls. So we allow access to kernel facilities only from outside of compartmentalized code. So one of the things that has to happen under the hood is that the compiler has to clear unused registers in the function signatures so that we don't accidentally leak information between the caller and the callee. We can't rely on the underlying hardware to do this because it doesn't know what the function signatures are. Right? We have to clear unused argument registers and unused return registers. All of this can occur at effectively a constant overhead to functional call cost. So we're going to take an additional exception. We're going to run a few more instructions, but they're relatively lightweight. So we have built a hardware-software prototype of this. So we implemented, using the BlueSpec hardware description language, a 64-bit pipeline processor using the 64-bit MIPS ISA. We also have our CHERI extensions to it. It is a mature but small processor, which to say it is not superscalar, but it does have a memory management unit and L1 and L2 caches. It is comparable to the processors you will find in small embedded devices. And we synthesize this at about 100 megahertz on an off-the-shelf Altera FPGA. We also have a complete software stack on top of this. We've modified the FreeBSD operating system to support fine-grained memory protection inside processes, the domain switching model, debugging features, and so on. We've also modified our compiler, Clang and LLVM, to generate CHERI instructions for memory access using a variety of ABIs. And then we've adapted a number of applications to use these features, which we use for the purposes of evaluation. And we've also released all of this as open source on our website. So if you wish to look at the reference design in hardware and software, you're welcome to do that. I only have a couple of minutes remaining, so I'll just tell you very briefly about the performance characteristics. So our goal was to try and provide extremely low-cost domain switches and also provide scalability on the number of sandboxes or objects that we're able to instantiate at once. This may be the bit where I do have to use the laser pointer. Well, if you look at the bottom two rows here, what we've done for the purposes of this graph is normalize things with respect to ordinary function call cost, which is a small number of cycles in the sort of 6 to dozen range, depending on stack manipulations and so on. The bottom green line here is CHERI object capability invocation, which is to say we are at all times within an order of magnitude of the cost of the function call and often closer than that. As you move up the cost in the graph, so these are cycles on the y-axis linearly, you hit a series of function calls which are done using the Unix IPC mechanisms, but using shared memory explicitly using the paging mechanism. And then we move to the top of the graph, we have using traditional Unix IPC without using shared memory facilities. The x-axis on this graph is the payload, which is to say the amount of data being shared by the caller and the callee. Of course, the left side is interesting because this has to do with the absolute minimum cost we can get away with. This is the no-op call, where we are paying only invocation overhead. And the right-hand side, as we shift out, is as buffer size is increased. And of course, the interesting observation is that we effectively have a linear cost over a normal function call. On the right-hand side, as TLB space runs around, you see the variance kick up, but roughly the same scale. Everything else is at least an order of magnitude up, and in some cases, it simply disappears from the graph. So we've accomplished our goal in terms of rapid domain switching. wanted to mention very briefly a couple of implications for application structure once you have the ability to perform extremely fast domain switching. So we've restored the single address space programming model, which means programmers now work with pointers and so on in their C language programs. This means they can easily debug them, reason about their behaviors and so on. We also use a referential integrity model, which matches the programmer model for how you use these facilities. And it's a relatively modest programmer cost in order to insert these protection domain boundaries. We're able to label functions as, this is a call gate. This structure supports mutual distrust, and it has an extremely low constant overhead. So we're able to perform interactions that would support, for example, extremely granular microkernel decomposition of conventional operating system kernels if we chose to pursue that. There are, of course, some downsides, or at least some challenges. One of them is that it is still hard to compartmentalize applications. It is much easier to program them, they perform well, but somebody has to reason about the security implications of shared memory and interacting components. We can't take that work away just by improving the hardware, but we can make it possible to scale up the use of compartmentalization dramatically. It is also the case that you now potentially have more shared memory. So high performance compartmentalized applications do use memory sharing, but lower performance ones tend not to. And reasoning about shared memory versus message passing is quite a different experience. A couple of other comments. The capability overhead is measurable. We do actually grow the size of the pointer. This is something that has to be managed and mitigated. And there are subtleties in how you structure code. And of course, by introducing more sharing, we actually emphasize some other security problems, such as the possibility of side channel attacks, which have to be considered separately from this ISA level approach. So let me just conclude by saying that we've implemented what we describe as a hybrid object capability system, which is to say we're able to run this within the context of existing operating system designs with only modest changes to hardware, that it integrates very nicely with the existing models, that we're able to do it in a way that is friendly to C language programs and shift away from quite hard to use inter-process communication, and we are able to realize literally orders of magnitude performance improvements for compartmentalized designs. And I'll just conclude by saying we do have an open source reference implementation and a complete description of our ISA up on our website. So thank you very much.
Thanks a lot.